joining us today for this event. We'll start. First, I would like to invite Professor Stavros Malas, the President of Cyprus Institute, for a very short introduction.
Very short. You know, I linger on a bit. Thank you. Okay. Dear Minister, thank you very much for being with us today. Esteemed colleagues, well, it is with great pleasure that we inaugurate the third ERA chair in this institution. And that really marks the success of the Cyprus Institute in securing these grants that come under this umbrella of structuring grants. For those that have not followed the European Commission funding schemes over the last 10 years, the European Commission has implemented a program for structuring research in the weaker countries of the Union. So the teamings, the twinings, the ERA chairs all come under this umbrella. Of course, you know very well that this institute has benefited enormously. Indeed, Cyprus has benefited enormously, and it is really a great achievement. And I really want to thank those who achieved this, and primarily Dina Alexandrou, Professor Alexandrou, for being able to bring two ERA chairs to the Institute, and that's really to her credit. We will continue on that. You know, we are very active in these structuring grants, and that's hopefully will bring us a lot more support. Now, I take the opportunity, since this is the last presence of Minister Kokkinos in his capacity as Deputy Minister for Science, to thank him. We'll help you later on to celebrate with us your birthday, which is his birthday today, yes. To thank him, you already got the first present from Dina, yes. So to thank him for his strong support and meaningful support during his tenure as Deputy Minister. He has been, I have to say, instrumental in shaping some key recommendations of the Review Committee. You heard me the other day, briefing you about the recommendations of the Review Committee. Minister Kokkinos was questioned or contributed to the discussion by the committee, and he gave some specific recommendations in his capacity as Deputy Minister of Science, and those recommendations made their way in the document, and I want to thank you for that, because that's really what's going to help us collectively to go to the government and hopefully reshape our relationship. So with that, I want to wish you all the best, not only for your birthday, but all the best for the future. And I know very well you will be with us in one way or another, because he has been a member of the Board of Trustees. And of course, in that capacity, he was also extremely helpful. Welcome. Thank you very much for being here, Gyriakos.
Thank you, Professor Malas. And I would also like to invite Mr. Kokkinos, the Deputy Minister of Research, Innovation and Digital Policy, to say a few words for the event today. Thank you.
Thank you, Stavros. Thank you all for inviting me in this very important event on quantum computing, which is deep in my heart, as I'm coming from the ICT sector, and quantum computing has been very prominent in the recent decade as one of the key advancements in technological advancements in the information technology domain. I don't know, but every time I am in this area, in this geographic location, I feel like home. Probably it has to do that, as you probably know, this used to be one of the first colleges in Cyprus. It was the Higher Technical Institute, a college, and I graduated from this college, and I've been in these grounds for 3 years of my life. I met my wife here, who was my colleague at that time, and my girlfriend, and I'm still with her, happily. I've been in the Board of Trustees for almost 10 years. As a minister, I've been in this fabulous technology and research institution many times, trying to collaborate, try to encourage, trying to facilitate, try to support the work of the Institute. And I think that today we're celebrating another big success of the Institute. So I feel like home, and irrespective of my future endeavors, rest assured that I will continue to be a strong supporter, an ally, and a friend of your work. Coming to my speech now, I would like to say a few words about the event of today. So it's a great pleasure to be with you today to launch and celebrate yet another outstanding achievement of Cyprus Institute. Please allow me to start by congratulating the minds behind this great initiative, Carl and Konstantia, and wish you best of success in this bold and challenging endeavor. Being awarded its third in total Yuhua Chair and second for Castor C bears testament to the capacity and quality of the research work developed by the Cyprus Institute, and particularly in the field that represents a huge leap forward for global science and technology. Dear friends, in recent years, there has been a rising interest in quantum computing, fueled by several breakthroughs on the technology side and a significant increase in investments. A whole generation of new quantum technologies is starting to emerge with the potential to produce concrete solutions to global challenges that will take even today's fastest computers hundreds of days, if not years, to execute. To unlock the transformative power of quantum, the European Union has already deployed a number of coordinated efforts to achieve the digital decade goal of delivering the first computer with quantum acceleration by 2025. Projects like the Euro HPC, joint undertaking, and other initiatives within Horizon Europe, and which aimed at accelerating the creation of new knowledge while facilitating knowledge transfer and advancing synergies between member states. Cyprus cannot risk and would not fall behind on this quantum revolution. Hosting an Yuhua Chair in quantum computing can contribute significantly to bridging the gap with other countries and advancing our country's posture as a regional science and technology hub. The Quest project will complement other ongoing efforts such as the CYQCI project for developing the first quantum communication network in Cyprus, while also capitalizing on the role of Castor C as the national high-performance computing center of the country and deepening the institutional with a wider European and international quantum community. In addition, the partnership with DESI Institute and the experienced leadership of Dr. Hal Johnson will further strengthen quantum research in Cyprus, providing access to advanced know-how and infrastructure, opening up new opportunities for joint projects, and ultimately paving the way for innovation breakthroughs with far-reaching economic and societal impact. In this long and exciting journey, my ministry will be by your side, supporting and facilitating the development of your activities, and I'm confident that under its new leadership, the Cyprus Institute can continue to evolve, reaching even greater heights and serving our economy, society with dedication. Thank you very much.
Thank you, Mr. Minister. Now I would like to invite Professor Constantin Alexandrou, the Principal Investigator of Quest, to give us a short introduction on the project. Thank you.
I would like to welcome you from my turn as well, and thank you all for coming here, and specifically the Minister, Mr. Kokkinos, thank you very much. This shows your engagement in the promotion of science and technology, and thank you for honoring us with your presence today. I would like also to thank, of course, my dear colleague, Carl Jansen, for taking this adventure and coming here to help us build the quantum computing knowledge and technology. So what I would like to do now is to give you a few highlights of the project. So what was our motivation for putting in this project? I show you here a very beautiful picture of the IBM quantum computer. This exists at the IBM headquarters. And of course, we all read that quantum computing holds the promise of enabling cutting-edge research across many fields, from physics, chemistry, to biology, computer science, as well as engineering. There is also huge innovation potential and scientific potential. I come from fundamental physics, and it's very exciting because we need such instruments to discover, for example, new physics that we don't know today. And this was our motivation, and I believe Carl's motivation for starting this endeavor. But it can have also a lot of other applications relevant for society, like speeding up financial calculations, making aircraft more efficient, discovering new drugs, improving batteries for energy storage, and accelerating AI applications. Currently, the basic problem is the limited number of qubits and the fact that they are noisy. However, technology is progressing very rapidly, and thousands of error-corrected qubits are foreseen by 2030. Therefore, it is urgent that we now have the knowledge and be able to exploit them when they come online. And this was the main motivation for this project, because in Cyprus there was nobody really that had this know-how to exploit the new technologies, and we thought we should do something about it. So the main goal of Quest is to contribute in making Cyprus quantum ready to harvest the unprecedented potential of quantum computing. How? Well, through the expertise of the ERA chair, that is a staff member of the German electrocyclotron research center in Germany. We will engage with other research groups, and I see some of my colleagues here from the University of Cyprus, and I thank them for being here with us. It will explore synergies in quantum computing. For example, as the minister already mentioned, the quantum communication infrastructure, where the ministry has been instrumental in initiating. So how we will do all this? The main components of the project is to establish a research group in Cyprus to pursue world-class research. The ERA chair, Professor Jansen, will be at a 40% appointment here at the Cyprus Institute, and the transitioning to 25% when an assistant professor will be recruited to lead the activities. We are in the process of recruiting postdocs and PhD students, so please announce this to anybody interested to joining us here. We will establish a quantum computing hub in partnership with the corresponding center at DESI that Professor Janssen has initiated and leads at DESI. CASTOC will become a member of the DESI IBM Quantum Network. This is very important because this will give us privileged access to cutting-edge hardware that we do not have right now in Cyprus, so that all academic groups, and I stress this, all academic groups in Cyprus can have access to state-of-the-art quantum computers as well as abroad. This is extremely important to jumpstart the activities. Beside academic groups, industry can also have the opportunity to use this quantum hardware. So the Q-Hub will serve as collaborative platform for joint projects and innovative ideas, interconnect researchers from research institutions in Cyprus, forge collaborations, pursue applications with industry, and target, of course, new funding revenues for sustainability. So this is the concept, really, of the activities that we will be doing. As you see, training and education is central because we want to educate young people to carry research and to innovate. And the topics of the research are, include quantum machine learning, for example, quantum algorithms, circuit design and error mitigation, development of use cases from various applications, and of course, access to quantum hardware to run them. We also foreseen activities to transfer knowledge beyond the researchers via, for example, co-development with industry, and as we said, helping industry to access quantum hardware. And all this will be done in partnership with the Center for Quantum Technology and Applications on DESI, where we will learn from them how to run such activities and adopt their best practices. We will have exchanges of staff, co-supervision of students, and common projects. And I see people here from DESI, and I'm very happy that they have joined us today. Thank you very much for traveling here. Okay, so to conclude, we will create a research group in quantum computing, engaging also researchers from other institutions, promote technology applications of quantum computing through the partnership of the corresponding center and DESI, train researchers in quantum computing, including researchers from other institutions, and pursue outreach and raise awareness in quantum computing research and innovation potential. So with this, I thank you very much, and I'm looking forward to hearing our air chair.
Thank you, Professor Alexandrou, and now I would invite Professor Janssen to dive us into the world of the quantum computing.
Thanks a lot to bring me here as an ERA chair for 5 years. And thanks a lot, Dina, that you convinced me to do this. You know that I was very skeptical because I have the center in Germany, but you finally convinced me that it would be a very good idea to come here and help you to bring quantum technologies, quantum computing to Cyprus. How can I page? Okay, thank you. What I want to do today is I again want to say something about the ERA chair. I have to become familiar with this. I want to give you a short introduction into quantum computing because I realize this is really something new here. And then I want to show you some applications, things that we are doing already now in quantum computing and things that we are really running now on the quantum hardware. I'm not talking about science fiction here. I'm not talking about something that we will do in 5 or 10 years. I will be talking about something that we do already now. And then I will conclude. Quantum technologies are really one of the highest priorities in Europe and worldwide. And for example, at Helmholtz, which is the big mother institution also for DESY, we have come together and we have developed a roadmap for the next 5 to 10 years, what we want to do in the Helmholtz Association. So we have a very clear plan in Germany at the Helmholtz institution, what we want to do. And this is researching the second quantum revolution. Because quantum computing on a quantum computer, this is now the second quantum revolution. There is already now a European flagship which has more than 1 billion euro, and I haven't put a number on the slides, but there will be another call where the European Union will issue 15 billion for quantum computing. Germany alone has invested 2 billion euro only in 2022, 2 billion euros, and more will come. So this might give you a flavor of what is presently happening. This is the ERA chair. I think Dina gave a very beautiful introduction into this. So we want to really build up a quantum computing group at the Cyprus Institute and through the Cyprus Institute in Cyprus itself. We want to develop applications of use cases for industry, academia, but also for governmental agencies. We want to develop algorithms and methods, and then we want to act as a hub for the Eastern Mediterranean region to really bring quantum technologies, quantum computing to the region. And I'm dedicated to help to realize this. We want to provide training in quantum computing. We want to educate also here young people in quantum computing. And Dina mentioned my students from DESY who are here. And this is now a generation, they start thinking quantum computing, which is really fantastic. And the ERA chair is really deeply connected to the Center of Quantum Technology and Applications. And let me just give you a short introduction. What is this? We got an innovation funding from the state of Brandenburg, and this is 15 million euros. We have 15 million euros over the next 5 years to build up this center. And through this money, we now have privileged access to quantum computer hardware at IBM. We have access to all the quantum computers they have, also the newest one, the ones that will come this year, and I will show you the roadmap of IBM, and we are guaranteed that, that we get access. And through this, we can, of course, also give access to the groups here in Cyprus, but also to industry and to other partners. And we are in the process of having the first industrial partner to give them access, and they are paying for it. So this will be our way of making the center sustainable. Also here, of course, we are developing applications for industry and academia. We develop algorithms and methods. And now comes a really important point, because we have these applications, we can benchmark, test, and verify emerging quantum computers. And this is also happening in Germany, in Zeuthen. People come to me and say, can you run your application on my quantum computer? I want to know how good it is. I want to know where it works and where it doesn't work. And I want to compare to the performance of IBM. And please find that my performance is better. Okay, and we have a quantum sensing element. So this sets the frame, what we are talking about. And this was in the last IBM Summit in New York, and their DESY with our center was really highlighted as one of the big achievements of IBM to find the partner that is really very, very relevant for them. And I like to show this because I didn't expect this, that this came out like this. So why is there this hype with quantum computing? And then you can look at the publications that are emerging every day, like 50 publications in quantum computing. And there are topics like quantum biotechnology. People are working on this. There are papers for evidence-based medicine. People are doing this already now. This is not dreaming. There are activities where people think about quantum batteries or for loan collection optimization. And then one day I found this paper here that even people are thinking about making quantum music. And then I thought, this is going too far. This is crazy. You shouldn't laugh, because my students convinced me that this is a good idea. And we made a paper about quantum music, and we will have in Berlin a conference about quantum music. And this is wonderful. This is really great. My students are laughing because they are listening to quantum music now, and this is really great. Okay, why a quantum computer? The reason is, besides the things that I showed you before, that all the systems that we have in high energy physics, in chemistry, biology, material science, or condensed matter physics are quantum systems. And Feynman wrote in his famous paper, "Nature isn't classical," I leave out this word, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. And this is what we are doing now. And the reason really is that, as Dina already mentioned, that with quantum computing, we have the potential to solve problems that are very hard or even inaccessible for classical computers. For the physicists in the room, this means topological models or non-zero fermion density to explore the early universe, or all these things. And we can look at corners of models, we can explore physics that we were dreaming of to tackle, and now we have the possibility. We are starting small, but now we have the possibility to do this. And I will show you examples. You know a bit in your computer, quantum computer, we use a qubit. Now, a qubit in a quantum computer, we are making use of quantum mechanics. In quantum mechanics, it happens that an electron, which you think of a solid particle, can behave as a wave. You shoot electrons towards such a screen, and what you see is nodes as if the electron would be a wave. On the other side, lights, where you think this is a wave, you have a light wave. If you shoot it on some material, it happens that you kick out some electron. So light behaves as a particle. And this is the principle of quantum mechanics, that quantum mechanical entities can behave either as waves or as particles. Why is this important? This is important because there is a difference between a bit in your computer, which can only have two states, 0 or 1, or a quantum bit, a qubit, which is a two-level quantum system with states 0 and 1. And a qubit is described by the states 0 and 1 with coefficients alpha and beta that add up in the square to 1. Forget about formulae. Think of a qubit as a switch that you can only switch on or switch off, and think of a qubit as a dimmer that you can really turn as you like. It can have any position. And now comes the point of why we are making use of the fact that quantum mechanical is a wave. Think of an orchestra. You have all the instruments, you sit in the audience, and you listen to the orchestra. You hear all the instruments, you hear the noise in the audience. And the reason is that you have a sound wave. And in the sound wave, you have superposition of all the instruments, of all the sounds that you get. You hear it very clearly. And this means that in the sound wave, you can store all the information of the orchestra. And this is now true for a qubit. I told you a qubit, a quantum mechanical entity, can behave as a wave. So it can also be in superposition. And like the orchestra, you can store an enormous amount of information. All the sounds that you have, all the information that you put into a quantum system, you can store simultaneously. And you can explore a much larger search space. Dina gets a Skype call that I'm saying something wrong here. I do not know, throw it away. So this is the first advantage of quantum computing, the principle, to make use of the principle of superposition, like with a sound wave. I made a very long walk back in Berlin to think about whether I find a nice illustration of the second advantage, entanglement. I failed. I discussed with my student, we failed. So take this as granted, what I now say. If you have two qubits, they can be entangled. This means if you act on qubit 1, it influences qubit 2. And it does this without any connection. There is no wire, there is no connection, no physical connection whatsoever. If you entangle two qubits and you act on one, you modify the other. And you can do this in principle over arbitrary distances. And this is one experiment here, published in this Nature, where they say they have some research station here on a hill, and they have a satellite, and the satellite is about 1,000 kilometers away. And they entangled two photons, one on Earth, one on the satellite, and every time the satellite crossed over, they could see that these qubits were still entangled. They could see if they do something with on the qubit here, the qubit in the satellite was modified. And this entanglement has absolutely no classical analog. It's nothing that we can understand in our brain. We can understand it mathematically, but to think about it is, I do not know, is hopeless. And this now means in turn that this can open completely new possibilities. And this is what we are after. Can we make use of these two quantum mechanical principles, superposition and entanglement, to do something that maybe today we even don't dream about? And this really opens the door to completely new directions. This is how a quantum computer looks from the outside. If you have 20 million euros, you can buy it, put it in your living room, and then forget, because they are outdated every year immediately. Some people in Germany have done this. I didn't say this, okay? This is the quantum computer from the inside. So you have all these apparatus that also Dina showed, and the quantum chip is sitting somewhere down here, and it has kind of the size of a chocolate, if you want to get a feeling. The chip itself down here is shielded to 50,000 times less than Earth's magnetic field. It's enormous. If I talk to the engineers at DESY, they are impressed by this. It's in a very high vacuum. The pressure is 10 billion times lower than atmospheric pressure, 10 billion times. And it's cooled almost 200 times colder than interstellar space. And this is all done to prevent any interaction with the environment. Because if a quantum mechanical system interacts with an environment, it is destroyed. It's not quantum anymore. You have to see that the chip down here stays by itself and is not affected by anything else. And this is what I told you already. This is IBM's roadmap. So now they have a 430 qubit machine. Next year, they will come up already with machines of 1,000 qubits. In 2024, they have machines with 4,000 qubits. And in the years 2025 and 2026, they will have machines with 10,000 and up to 100,000 qubits. And some of them are error corrected, which means that you can use the quantum computer as you use your computer now. They will give you the correct result. This is error corrected. When this happens, then we are really in a phase where we have overcome all the difficulties of quantum computers of today. You can really use it, and compute exact results. And Google promises that by 2030, they have 1 million qubits already. Thousands of them are error corrected. So you have a working machine. We are not talking about 2050. We are talking about 2030. And if I look at my young people over there, this will be your world. And how to quantum compute? Well, the program language is Python. This is something, as a scientist, almost everybody is using. It's nothing mysterious. It's simple Python programming. And you get a very convenient setup. You get simulators. The companies provide simulators that you can install on your local laptop. And there you can develop your programs. You can test your programs. You can verify your programs. And once you identify it is correct, it's a single line in your program and it goes to the real hardware. It's very convenient. And on the hardware, you can then access the machines through a reservation system, which my people are often complaining about because so many people are now using the machine that the queue is very long and we wait for very long. But we have this privileged access also. And there is a lot of documentation. There are many, many tutorials and examples. And there's, for example, this IBM textbook where they explain Qiskit and many quantum algorithms, which really means that if you're interested in this, you can start now. I have summer students at DAISY. They are staying 8 weeks. When they leave, they have made runs on the quantum hardware. This is nothing totally mysterious. Of course, if you do more complicated things, it takes longer, but the principles is there. So what can we do? So this is one example, what we are doing, also with Stefan Kuhn, who is in the audience, who came from DAISY. Thanks, Stefan, to come here. And this is the flight gate assignment problem. So you have an airport, and you have incoming and outgoing flights, and you have passengers that want to change the flight, and you want in the set of all the flights and gates, you want to find the smallest connection, the shortest path for all the passengers to change the flight. Okay. This is a classical optimization problem, and this is something where I'm personally extremely interested in to see whether we can reach here a quantum advantage. Because, I will say this later again, the mathematical formulation of this problem is basically the same if you have problems in logistic, in traffic, and all these things. So once you solve this here, you also solve problems in logistic, traffic, in all the problems where you have a classical optimization problem. A bit of mathematics. Sorry for Tanya, Sophia. No, I know that you will understand. So you define a variable, which is 1 if a flight is assigned to a gate alpha and 0 otherwise. You transform it to a -1 and 1. This is an eigenstate of the third Pauli matrix. It's a 2x2 matrix. And from this, you can formulate something that we call a Hamiltonian. I will not go into the details, but you can mathematically formulate this in such a form. And then the task is to find the lowest energy of this object here. And this corresponds to the shortest path. So this is the mathematical formulation without giving details. And as I said, the same mathematical description, the same form applies for problems in traffic, logistic, particle tracking. The only thing that changes are these coefficient matrices Q. The rest stays the same, and you can use the same algorithms, the same methods to solve problems from here. So we did this, and I got a new postdoc, Yuhua Chai. She really found some very good improvements, which I cannot explain here. But what I want to show is that with our old approach, so what is this here? This is the number of good solutions that you are finding. And what you want is that this is basically 1. In our old approach, we saw that this is declining very rapidly, and we were almost given up. But then Yuhua came and said, I know these improvements here, and now you you see that as a function of the number of qubits, which is the number of lights times gates, this good solutions that you find is close to 1. So you basically always find good solutions for the airport. You find the shortest path up to, at the moment, we have, this is 14, but today we have like 20 qubits already, and it stays like this. I will not go into this here. Another problem is particle tracking. And Tim, who is sitting in the audience, who also came, thanks Tim, to Cyprus, and he is looking into this. So this is when you are at CERN and you have one particle event, then you have such a mess. And you want to identify where are the tracks of the particles. And this is a real challenge for CERN. In the next installation of CERN, they expect such an amount of data that they are doubting that they can solve this with classical computers. And therefore, at CERN, together with us, they are looking at possibilities to solve these problems with quantum computers. Okay? And Tim and the others, we set out and we formulated this Hamiltonian that I showed you before for such a problem. And again, this is, we call it here precision, but this is basically the number of good solutions. So you want to be close to 1. And this is as a number of the qubits. So here you have like 500 qubits. And as I told you before, 500 qubits will be there next year. If you have 500 qubits, you are here. And what you can see is, if you go along this line here, this is CERN today. So you could identify these particle tracks with a very good precision now. This is our projection for the next phase of the LHC. And you see already with 500 qubits, even if you have a huge amount of data. So this is the number of particles per event. So here we are in the thousands, here we are in the 10,000s. This is the big challenge. And you see that even for this case, we find very good solutions already now. We are also doing classification, and this we are doing together with Maria. She is also here. Thanks that you came, Maria. And Maria is actually now enrolled in the Cyprus Institute, so she is here. And with Maria, we want to identify lung cancer in a very early stage, meaning we want to identify lung cancer using genes and exons. Exons are the active regions on a gene. And we want to identify the bad and the good genes and exons. And we want to do this with something that is called a Boltzmann machine. A Boltzmann machine is used already now as a machine learning tool. I'm not able to explain this here. And our idea with Maria is now, she has done this in her master thesis with the classical Boltzmann machine with very good results. And our idea is now to bring this on the quantum level, to do lung cancer classification on the quantum level. How far can we come? Can we outperform the classical Boltzmann machine? That's our task. This is what we want to see, and this is Maria's PhD topic. And Maria, you show that we have an advantage, right? I want to tell you a little story where we actually started with quantum computing in my group with Stefan, with Tobias Hartung and Lena Funke. So this is, again, a mathematical model. It's called the Heisenberg Model, and you have basically, so this I is a lattice point, and you have interaction between nearest neighbor lattice points. This was invented by Heisenberg in 1928. It's not the newest model on Earth. This is a mathematical microscopic description of magnetism. So with such a microscopic model, you can describe magnetism. It's interesting because already this model, which lives in one space dimension, has a phase transition from an unmagnetized to a magnetized phase. The mathematical structure of this model is typical for lattice gate theories. And what is interesting here, you can study such models on lattices of 1,000 sites, but you can also study it on lattices, let's say, with 2 sites, which means that you have a very simple mathematical model that you can run already now on a quantum computer. And this is why companies like IBM and others come to us and say, you have this prototype model. Can you try this out on my machine? What comes out? What do we have to improve? Does it work at all? or not? So we did this. So this is the energy that you want, the minimization of this Hamiltonian that I showed you before. And this is basically as a function of the number of iterations in the algorithm that we use. And this dashed line here is the exact result. So we programmed this model in Qiskit in the language that is used at IBM. We put in the algorithm and we saw, yeah, it is converging, it is converging, it is converging, and it is converging to the right value. So we were very happy. We did it. Now, this is an exact simulation. A quantum computer is noisy. You have all kinds of noise. You have readout noise. Sometimes the things that you computed is read out wrongly. Sometimes the qubit is not working correctly. So you have a lot of noise in your quantum computer. But the companies, especially IBM, they provide you with noise models. They provide you with noise models for all their machines. They have like 20 machines that they give publicly, and they have for all these machines, they have noise model. And you can switch it on in your program. So after this, we did it. We switched on the noise, and you see, fantastic, it converges, it converges, it converges, but it converges to the wrong value. And this is the effect of noise in the quantum computer. And then we scratched our head and said, can we repair this? And now I can only flash what we did. So we did two things. At the end of a computation, you get a bit string, which is ones and zeros. And sometimes when you read out such a qubit, instead of the 1, you get a 0. Or if you have a 0, you get a 1, and so on. And with these people here, again with Stefan, who is here, we found an analytical way to correct for this error. So we know analytically how we can compute the correct readout process. And the other thing is that we did, and this is really very mathematical, a dimensional expressivity analysis of quantum circuits. So for people who know it, this is a quantum circuit, and we were asking ourselves, are there maybe gate operations that are not needed at all? And through this dimensional expressivity analysis, we could identify these 4 gate operations here as being not necessary. We could simply leave them out. And this is, again, an analytical method how to do this. And what I really want to emphasize, these 2 methods, these 2 algorithms are developed from applications in fundamental research. But, of course, these methods, these algorithms, they can be used for any algorithm that is running on a quantum computer. So you see that from fundamental research, you can really develop things, and this is what we want to do here in Cyprus also, with the error chair, that you can develop things that can be used very broadly. And IBM is asking us, can't you implement this for us? And then, if you do the experiment again, you apply these 2 methods, then again, you run this, and you see it converges, and it converges, and now it converges to the right value by using these new algorithms and methods. I think this is very nice, and we are using it very often. I cannot resist to show you this slide because people here doing lattice gate series, and this is my favorite slide of the talk, because this basically shows that we are now studying a generic quantum field theory on the quantum computer. This is 2 + 1 dimensional quantum electrodynamics. I, again, will not go into the details, but I want to show you we are not only computing toy models, we are really computing generic quantum field theories already. And what we do, together with my student Ariana and my postdoc Giuseppe, we are computing physical things. We are computing something that is called a mass gap. This is a real particle mass. So if this would be QCD, we could compute already now the proton mass on a quantum computer. We can really compute physics there, non-trivial physics. And here's one example. This is a certain observable. It doesn't matter what it is. And we follow this as a function of the coupling of the model. And what you see is when you change it, you see this dip here, and all of a sudden it jumps. And we interpret this as a first-order phase transition. And the point is, this is now computed in a situation that is not accessible to classical Monte Carlo methods. It would not work in classical Monte Carlo methods. This is only doable with quantum computing. So this is one example where you see already now that quantum computing can do things that you cannot do classically, if the system would be large enough. This brings me to my summary and outlook. I think it took 40 years to start realizing Feynman's vision of using quantum computers. Now we are there. We have them, we can use them, and we are using them. And quantum computing really offers the fascinating possibility to address applications that are very hard or even not accessible to classical computers. And we are investigating whether this potential that quantum computing has really leads to a quantum advantage. It's totally open, but we are trying to see this. And presently, I would say we are researching the second quantum revolution. We want to see where quantum computing can be useful, which is again manifested in this Helmholtz journal. For quantum computing itself, we are at the moment identifying and evaluating applications for quantum computers, like the examples that I showed you, lung cancer classification, flight gate assignment. And we are developing algorithms and methods to be ready when we have the first error-corrected quantum computer. In the midterm, I think we will employ quantum computations for solving problems, most probably through a hybrid quantum classical algorithm, so you need always a classical computer aside the quantum computer. And maybe if you let me dream, in the long term, we use quantum computers routinely in our daily life. And thanks for your patience and your attention. Shall we allow for questions, or?
Absolutely, yes.
So we allow for questions, if somebody dares. There's one.
How disruptive technology would this be for our civilization? Good disruptive. So the internet was a good disruptive technology. What do you rate quantum computing to be when it comes out?
Well, as I said, if we have, with present quantum computers and even more with error-corrected quantum computers, we are in the position to solve problems that you are not dreaming of today. This will be so disruptive that you cannot imagine. It's really, and I cannot tell you where now the big quantum advantage will come, but it's pretty clear that we are working towards this, right?
A technical question. How do you maintain minus, if I'm not mistaken, minus 217 degrees? The chocolate bar.
Oh, this is, I'm not a hardware expert, but I learned that this is a long process to cool down these machines. They do it in several processes. They have several ways of cooling it down. I do not know, to 50. Then from 50, they go with another fluid. They go to minus 150. And then finally, so this is really a step process. It's not like you put it in the fridge and then you wait. No, it's like a step process that you come down to these temperatures. But I cannot give you the details of this. People are getting warm, very good.
There are concerns about using quantum computers to crack security.
Is the microphone on?
Can you hear me?
Yeah.
No. Yeah. Okay. There are concerns about using quantum computers to crack security systems.
Oh yeah, sure.
What's your point of view on that? Considering that if you can use quantum computer and break encrypted algorithms, that it will take years with normal computers.
Yeah, definitely. Definitely. There is this Shor's algorithm where theoretically it is shown that the quantum computer has an advantage and that you can really, you can hit any security measure, any encryption, and make it useless on the classical level. I do not want to do this here, but maybe I want to do this. Wait, I can. So, and there are really So there are people trying to evolve this algorithm. It's very hard to implement at the moment, but they are trying to evolve it such that it becomes practical. And there are many companies who counteract and say, we want to build, we want to invent, we want to develop quantum-safe encryption algorithms. So this is going from both sides. And the question is, who wins the race, right? Save your money under your bed, maybe. There was Sesam.
Okay, so thank you very much, Carl. So I have many questions, but I will stay only a couple. Just from a curiosity, you have only a few qubits that are error-free, right?
At the moment, we don't have any error correct.
How can you use the rest? I mean, in general, can you comment a bit on this description? Because you say initially that you expect thousands of qubits, and only a few of them are error-free. The machines, the hardware.
So you have to really differentiate between the two phases. At the moment, we don't have any error-corrected quantum computer. They are all noisy.
They're still all noisy.
They are still all noisy. This is why we need these methods like this error mitigation. There are several error mitigation methods. Once in the second phase, when we have error-corrected quantum computers, we have 1,000 qubits that you can use for your computation, and all the rest of the qubits you have to use to error correct. There are algorithms and methods how you really do error correct. And this is a fantastic problem, because you have to do this error correction without disturbing the system. Once you disturb the system, once you read out a qubit, your calculation is gone. But there are error correction algorithms with which you can do this.
So the idea is to decompose the hardware, let's say, for these two different
Yeah.
operations.
Yeah. Mm-hmm.
And the second point might be a bit technical, but in most of the cases you present Hamiltonians that are discrete-based, Isaac type. What about when you have continuous variables?
Continuous variables, good question.
Do you foresee that this is something that can be addressed within the next few years?
I don't know. So at the moment, what we are doing when we have continuous variables, we discretize them and we truncate them, and we investigate what discretization and what truncation we need to come to the continuous variable. So when do the results not change anymore? That's maybe a little bit stupid, but the only way that I know at the moment.
Whether this is applicable as a generic strategy.
You have to find a discretization and truncation scheme for your problem. But we know this for gauge series, how to do that.
Carl, thanks for a nice talk. I would like your perspective on the issue of modularity. So for computational systems, it's very important to be able to decompose them, as you know, into different modules so that module A doesn't interact with module B. And I was wondering, this whole notion of entanglement, I mean, it's the power behind quantum computing, but is it also the weakness in the sense that how do you build modular systems if they are entangled?
Okay, so here's this little word parallelized. So how will quantum computers with 10,000 or 100,000 qubits be built? They, for some technical reason that I do not know, they cannot go beyond the size of the chocolate. So if you want to have 100,000 qubits, you have to have several chocolates. And now comes the question of entanglement. And there you can, at the moment what IBM is doing, and I only know about IBM, is to classically connect these chocolates, but then through algorithms, they can connect them. And you get the full system. There's a certain quantum algorithm also invented by IBM, I believe, where even through classical connections, you get the information from the full system. What they also are developing, but I think they are not yet there, is really that they have photonic lines between these chips. And through these photonic lines, you can really transport quantum information, and you can keep full entanglement.
The chips themselves are not entangled? The different chips are not?
At the moment, when they have these classical connections, no. When they have these photonic connections, they are entangled. And they can do this over distances. This was shown in the workshop we had last year at CERN. They're really working on this. what Google is doing, I have no idea. This is all behind the door. Sesam, you still have a question? Yeah, why don't you just shout? Absolutely. I'm working together with Ivano Tavernelli from IBM, who is the head of IBM quantum theory, and he is coming from quantum chemistry. And they are doing already rather large molecules. And actually, we from high energy physics, we are learning from them, because they have already invented a lot of algorithms and methods where they solve chemical systems. If you're interested, there's a very nice review where all the ways are described, how you can tackle chemical systems, molecules, whatever you like. And this is an industry by itself. For example, IBM, they have a library. They have a quantum library for chemistry. They have fully developed codes. So this is something that exists. And I'm working myself on another chemical system, and at the moment we go to 10 qubits or so, but I think we can enlarge this. This is certainly possible. This is besides high energy physics, I think this is one of the prototype applications that we have.
Hi, thank you very much. Extremely interesting talk. And I apologize if my questions are a bit basic. I'm not a physicist, but my question is specifically regarding entanglement. When it happens, is it temporally limited? Is there a temporal, so once two particles are entangled, do they remain entangled eternally? And is there any evidence that entanglement happens? Is it a completely artificial effect, or does it happen naturally? Are particles entangled naturally?
Mm-hmm. This is a deep property of quantum mechanics. And as I told you, we can describe it mathematically in a very clear way. If you start thinking about it, I think this is your doubt, right? You are starting thinking about it, and then it sounds really completely mysterious. But this is really a deep property of quantum mechanics. You're exhausted. Me too. I think we have beer and wine, and I thank you a lot again for your attention.
Thank you very much, Carl. I now invite everybody to join me in wishing the minister happy birthday. So we're going to sing some quantum music. Happy birthday to you. Happy birthday to you. Happy birthday, Kyriakos. Happy birthday to you.